This online tutorial is about acidic basic strength of alcohols. Alcohols are organic compounds in which a hydroxy group, OH group, is attached to a saturated carbon atom. Generally, we can represent them as R3COH with this structure. Here, R is an organic group such as an alkyl group or an arene group. It can also be hydrogen. In addition, these R's can be identical or different. For simplicity and ease, we can also represent alcohols as ROH. Where it is important to consider that in alcohols, OH group is attached to a saturated carbon atom, to a sp3 hybridized carbon atom. For alcohols, we can consider the following two conjugate acid-base pairs: ROH2 plus ROH and ROH RO minus. For example, the acid dissociation reaction for this pair is in this way, while for this pair, acid dissociation reaction is like this. In this pair, alcohol itself is the conjugate base. Its conjugate acid is ROH2 plus, the protonated alcohol, which is called alkyloxonium. In this pair, alcohol itself is the acid, the conjugate acid. Its conjugate base is RO minus, the deprotonated alcohol, which is called alcoholate or alkoxide. For example, we have the alcohol methanol, CH3OH. The conjugate acid of the methanol is CH3OH2 plus, methyloxonium. The conjugate base of the methanol is CH3O minus, methoxyl anide. For this pair, the value of pKa is about -2, while for this pair, value of pKa or acidity pKa of alcohol as an acid is about 16. From one alcohol to another one, values of these pKa's can change. For example, here for one alcohol, we might see a value of 15.5 for pKa, while for another alcohol, we might see a value of 18 for pKa. Therefore, here it is better to consider ranges such as the range from 15 to 18. But for simplicity and ease, we can also consider a single value such as these ones. It is very useful to compare acidities or basities of alcohols with water. In aqueous solutions, we can consider this graph. Here, acidity increases from bottom to top, or value of pKa decreases. Let's assume that water is here. Then we will have alcohols here. And here. Based on graphs such as these and values of pKa's, we can see that as bases, alcohols are weaker than water. Or in other words, the conjugate acid of the alcohols, alkyloxonium cations, are stronger than hydronium cation. Based on our discussion about leveling effect of antibiotic solvents, here we can say that alkyloxonium cations are strong acids in aqueous solutions. They will be level with the conjugate acid of the solvent. Their dissociation reaction will be complete, and therefore we can neglect basic behavior or protonation of alcohols in aqueous solutions. On the other hand, here we see that as acids, alcohols are weaker than water. Or in other words, the conjugate base of alcohols, the alkoxide anion, is a stronger base than the conjugate base of the solvent in aqueous solutions. So alkoxide anions in aqueous solutions are strong bases. The base dissociation reaction is complete, and therefore we can neglect acidic behavior or deprotonation of alcohols in aqueous solutions. Since acidity and basicity of alcohols in aqueous solutions are outside of the two extremes of the solvent, alcohols are almost neutral in aqueous solutions. There are neither acids nor bases in aqueous solutions. However, since here these two pairs are not that far away from each other, we can consider that in some situation we can have acidic or basic behavior for alcohols in aqueous solutions, of course, to a small extent. In aqueous solutions with high concentration of H+, in very acidic aqueous solutions, a small fraction of alcohols can be converted to their conjugate acid. A small fraction, such as 1%. In aqueous solutions with high concentration of hydroxide anion, in very basic aqueous solutions, a small fraction of alcohols can be converted to their conjugate base, to alkoxide anions. Such conversions are usually negligible, but they can be important for mechanisms of some organic reactions. Anyway, we see that alcohols are almost neutral in aqueous solutions, and in many cases we can neglect and ignore their acidic or basic behaviors in aqueous solutions. In solvents with higher Bronsted acidity, such as acetic acid, basic properties of alcohols will be strengthened and alcohols will behave as bases. On the other hand, in solvents with higher Bronsted basicities, in more basic solvents such as ammonia, acidity of alcohols will be strengthened and alcohols will behave as acids. So we see that by increase of acidity of the solvent from ammonia to water to acetic acid, behavior of alcohols as our solutes can change from basic behavior to neutral to acidic behavior. It is also good to consider that in addition to acid-base reactions, alcohols can have other reactions such as substitution and elimination reactions. For example, ethanol in pure sulfuric acids reacts in this way. Which can be attributed to protonation of ethanol by strong sulfuric acid, then separation of the water from ethyloxonium, then protonation of water to yield hydronium cation, and combination of the ethyl carbocation with hydrogen sulfate to form this ion pair. From one alcohol to another one, values of pKa's, acidity or basicity, can change. Many factors and parameters can affect acidities or basicities of alcohols. Like other oxo acids, here also electronegativity and inductive effects are usually among major factors in determination and comparison of acidities or basicities of alcohols. Let's consider examples in this regard. We can consider ethanol, 2-chloroethanol, 2,2-dichloroethanol, and 2,2-trichloroethanol. In aqueous solutions, values of pKa's are as follows: 15.5 for ethanol, 14.31 for chloroethanol, 12.89 for dichloroethanol, and 12.24 for trichloroethanol. We see that here acidity increases by increase of number of chlorine atoms. This can be attributed to inductive effects. Chlorine atoms are electron withdrawing groups by inductive effects. They are more electronegative than carbon or hydrogen. Electronegative chlorine atoms withdraw electrons from carbon atoms. Carbon atoms become more positive. It becomes harder for the oxygen of the OH group to withdraw electrons from carbon atoms. As a result, oxygen withdraws more electrons from hydrogen. Hydrogen becomes more positive and acidic. This increases by increase of number of electron withdrawing chlorine atoms. In general, increase of strength of electron withdrawing groups, increase of number of electron withdrawing groups, such as here, and decrease of distance between electron withdrawing groups and the OH group, all can result in increase of acidity. However, other factors can also be important. For example, let's consider 2-fluoroethanol, whose pKa is equal to 14.42. 2-fluoroethanol as an acid is stronger than the ethanol because its pKa is smaller, which can be attributed to electron withdrawing fluorine atom. However, as electron withdrawing groups, fluorine is stronger than chlorine. Yet we see that acidity of chloroethanol is higher than that of fluoroethanol. This can be attributed to other factor here. In 2-fluoroethanol, we can have intermolecular hydrogen bond in this way. intermolecular hydrogen bond between the fluorine atom and hydrogen of the OH group stabilizes this species, the conjugate acid, therefore reduces its acidity. In general, in comparison of acidities or basicities of alcohols or other species, things can be more complicated than what we might expect. Comparison of acidities and bases of alcohols with water in aqueous solutions and in the gas phase is a very good example of this. In aqueous solutions, water is more acidic than alcohols, as values of their pKa's can show this. Therefore, we have this order of basicity for their conjugate bases. We might think this is due to the fact that alkyl groups are electron donating groups. From water to alcohol, one hydrogen is replaced with one alkyl group. Alkyl groups are electron donating groups, so we can think that they will reduce acidity. While alkyl groups are electron withdrawing groups, and in alcohols they donate electrons, this order of acidity is not because of electron donation by alkyl groups. In the gas phase, we see that this order is reversed. In the gas phase, alcohols are stronger acids than water. Or for the order of basicity, we have this. So why this happens? Alkyl groups are usually electron donating groups. But why usually? Because alkyl groups can also withdraw electrons against negative charge, against positive charge. Alkyl groups are electron donating groups. But against negative charge, alkyl groups can be electron withdrawing groups. To see this, why this is like that, it is good to consider molecular Jaffe electronegativity, where electronegativity chi is equal to A plus B delta. A is the intrinsic or inherent electronegativity of the atom, or it is the electronegativity of atom when it is neutral, when the charge on atom is zero. B is the charge coefficient and delta is the charge on atom. Here we see that when positive charge on atom increases, its electronegativity increases, but when negative charge on atom increases, its electronegativity decreases. So we can consider hypothetical situations such as these ones. When both carbon and oxygen atoms are neutral, since oxygen is more electronegative than carbon, it will withdraw electrons from carbon. Carbon will become positive, Carbon will act as an electron donating atom and oxygen will become negative. When oxygen is positive, it will have even higher electronegativity, so it will even withdraw more electrons from carbon. But when carbon is neutral while oxygen is negative, we can discuss that this negative charge reduces the electronegativity of the oxygen so that electronegativity of the carbon is higher than that of oxygen. So carbon here will withdraw electrons from oxygen. So we see that alkyl groups can have both electron donation and electron withdrawal ability. Against positive charge, alkyl groups can donate electrons. Against negative charge, alkyl groups can withdraw electrons. So alkyl groups can stabilize ionic species, either negative or positive ionic species such as alkoxide anion or alkyloxonium cation. In addition, alkyl groups are large, bulky, therefore they are highly polarizable. Negative or positive charge can polarize them, can convert them to induced dipoles. Therefore, we can have ion-induced dipole interactions in ionic species such as these ones between our ionic charge and alkyl groups. So in this way also, alkyl groups stabilize ionic species such as these ones. As a result, substitution of hydrogen by alkyl groups from water to alcohols results in stabilization of ionic species involved here. In the case of acidity of alcohols, alkyl groups stabilize the conjugate base, which is anion. Therefore, they reduce the basicity of alkoxides in comparison to hydroxide. On the other hand, they increase acidity of alcohols in comparison to water in the gas phase. We have a similar situation in comparison of basicities of alcohols. In gas phase, due to inductive effects and polarizability of alkyl groups, alcohols are stronger bases than water. So these are inherent acidities and basicities. But while these orders are reversed in aqueous solutions, polar solvents such as water can have strong solvation effects. Especially water can form hydrogen bonds with species such as these ones. Here, ionic species such as these ones have an advantage over neutral species such as alcohols themselves. Water can form stronger hydrogen bonds with ionic species such as these ones because the ionic charge strengthens the hydrogen bond. Therefore, in aqueous solution, solvation effects work in the favor of ionic species. But presence of alkyl groups in ionic species reduces this. Alkyl groups are hydrophobic. They don't let nearby water molecules easily form hydrogen bonds with themselves and with alcohols or their associated acids or bases. Therefore, salvation effects are weaker for alcohol, for ionic species of alcohols here. Here, salvation effects work in the favor of ionic species of water. As a result, water becomes a stronger acid than alcohol. It also becomes a stronger base than alcohols. Here, salvation effects by water stabilizes hydroxide anion more than alkoxide anion. This stabilization reduces the basicity of hydroxide and increases acidity of its conjugate acid. And you can have similar discussions here. So we see that in the gas phase, alkyl groups help ionic species. But in aqueous solutions, presence of alkyl groups don't let salvation effects to help ionic species. And this results in these orders of acidities or basicities. Here it is also good to consider, as size of alkyl groups increases, as alkyl groups become larger, they can spread or disperse negative or positive charge over larger volume. Therefore, their electronegativity will be less sensitive to charge. Here, the charge coefficient for larger alkyl groups will be smaller. Therefore, larger alkyl groups are better at electron donation or electron withdrawal by inductive effects. This can be useful in comparison of acidities or basicities of different alcohols. This is the end of this online tutorial. I hope you find it useful.